We're starting the troubleshooting process on this PDP-8L computer. The board locations are identified on this chart. We've got the columns A, B, C, D, and the row numbers 1 through 36. So here are the columns A, B, C, and D, and then the row numbers. 1 is the front panel board, and then 2, 3 to 36. I've color coded it. I'm working in this area right now, this purple area, which corresponds to this second row and slot A and B. Now, the front panel consists of incandescent lamps driven by transistors, which in turn are driven by NAND gates. So you have here the various lamps, and they are driven by flip-flops on M220 boards, which are sitting right here. And I'm working on the first one, which is this purple one. So it's column A and B, because it's a double width board, and O2 is the row number, which is that right there. So these flip-flops here, which are distributed on 6 different boards, contain 2 bits each of the accumulator from 0 to 11, the memory buffer 0 to 11, the program counter bits 0 to 11, and the memory address buffer 0 to 11. The flip-flops are D-edge triggered. The data comes in on these circled lines: red, orange, yellow, green, blue, and purple. 12 bits. And then they're clocked. So there's a clock line for the whole row of flip-flops for the memory address, for the program counter, for the memory buffer load, and for the accumulator. The accumulator has a link, which is a 13th bit. Now, to test if the flip-flops are good, I need to put a prescribed set of data on these lines and then clock the appropriate register. Now, these lines are driven by this very complex major register gating. So that is just for these 2 red lines here, are these 2 here. That is the logic, and it contains all the logic for switch register, accumulator data. All the data is available for all the registers, and then the clock at the appropriate time in the timing cycle selects which register to operate on. So it's quite complex. There's carry bits, because you have auto increment on certain instructions, left double shift, right double rotate, all this sort of logic. So it's quite complex. So what I've done is disconnected these inputs. Now, these inputs are found here on this board and on this board. So I pulled them out so that I can feel free to tie these lines high or low without damaging any TTL driver chips, because I've removed the drivers. These I've located where these sources are from. They're on these boards, and I pulled them out. They're lying here. They came in from this area, from this blank area here. The other thing I had to pull out was the clock lines for the flip-flops, which were these, as we discussed before, these 4, and they are driven here. So I pulled these boards out as well. It's actually one board, an M617 in slot B08, and then of course all these lines here These are all driven by these. So I pulled this board out too as a M617 A08 and A09 and an M617 B08 and B09. So I pulled those all out. So what we have then, I made this special socketed wire plug, which can slip right over any pin on the wire wrapped back plane. So I've actually got wires attached now. These wires are these. We're actually working on the purple one, so let's move there. It's the same thing, but they're all in parallel anyway. So these lines here, these first 6 lines are here, and I've grouped them together so I can just ground them or put them to leave them open. And if you leave them open, then they are actually at TTL high level, around 1.6 volts. It's good enough. So let's start the machine. Now, with all these cards removed, this is the default setting of the flip-flops. So what we're going to do is ground these 2 clips. The chassis. And what that effectively does is ground all these inputs low. And since these are AND gates, since every one of them is low, it doesn't matter what the second input of these AND gates are, the outputs will be zeros. And if the outputs are zeros, an OR function is 0, and because it's complemented, it's a 1, and a 1 there will turn on all of these flip-flops, and that should turn on all the lamps. So let's see if that's true. So I've grounded the lines. We need to clock it. So the red wire is the memory address clock. Let's see what happens. I'm going to hit it now. There it is. All the lights are on. The orange wire is the memory buffer. So we're going to ground that to the chassis. Ready? There. All the lights are on. And the yellow wire is the accumulator. And I'm going to ground that to the chassis. Let's watch it. There. So the flip-flops, at least at this test, are all working, and we've got every light on, including the accumulator link. Now, unfortunately, when I take these clip leads off, they are at a level high. Let's just see what they are actually. Voltmeter. When they're floating like that, it's approximately 1.6 volts. So that still qualifies as a logic level high. So now if I hit these clock lines again, there's the memory address. They don't all go off, okay? There's the memory buffer. And here is the accumulator, the yellow one. So we have this strange middle section that's on, and the reason for that is that the middle ones obviously not all of these sets have a 0 here, and that means even though these are all high floating, all these lines are high, so we've got 1s. Apparently, the other half of the AND gates are still 0. And because there's at least 1 0 on these AND gates, we have a 0 at the output. That means a 1. Hold on a second here. These are floating high, but the outputs are still 0, which means the OR is 0. And complemented is a 1. That's why those lamps are still on. We need to turn on at least one of these AND gates in order to turn off a lamp. And the reason, I guess, is because we don't have a carry in the add, or the switch register, for example, is an input, or one of these lines is not low, because they're floating. I didn't tie these anywhere. I only did these first 6. So these are the next step. I got to buy more of these clips tomorrow. But this is how you start troubleshooting the PDP-8L.